study the notes that we're going to begin. It begins with our lab, understanding the content in the lab. The lab is really an introduction to section B of Unit 2. And then you'll take a quiz on this Wednesday when I'm not here. All the quizzes you're going to take are Google Forms, so that way I can grade them at home. Something for me to do. Okay, Mr. Walter is going to be checking your homework just like I do. He's going to come around, say, let's show the homework. You'll hear on the video, I will be going over the homework, so you'll be paying attention as he comes around to check your stuff. And it'll be just like usual. Okay, I just won't physically be here, but I'll be mentally with you. And then don't forget your test corrections. I have to talk to Mr. Canestracci, but I'm planning to send him down here Friday, right after school's over, to pick them up from the blue bin and drive them to my house, because it's like my family's camping out at my house. I'm like, so what am I doing Wednesday after my radioactive test? Cleaning my house, because there's going to be a lot of people there, which I'm not thrilled about. But it is what it is. All right, so he'll come and get them. So it's something else for me to do while I'm home. On vacation. It's not a vacation. All right, let's check this out. Yep, there we go. Okay, number 1 is 3. Number 2 is 3. 3 is 2. 4 is 1. 5 is 2. 6 is 2. 7 is 2. 8 is 3. 9 is 3. 10 is 2. 11 is 2. 12 is 2. 13 is 2. All right, 14 was the one you had to draw to scale with your ruler and your protractor. So let's check this out. I have white paper here for this. Okay, the first thing you had to do was draw the sequence of 2 vectors in the scale that you were provided. It should look like this, but let's measure everything out, just like I would be doing if this were your quiz. So you should have one arrow going up, arrowhead on it, one going to the right, arrowhead on it, labeled 200 meters, 300 meters. Okay, let's check the length of the one that goes up. With your ruler, check. That should be 4.0 centimeters of length. 4.0 centimeters of length if you did it correctly. 4.0 centimeters of length in this scale. Right, was 1 centimeter is 50 meters, so 200 divided by 50 is 4. Then the one going to the right, measure that length. That should be 6.0 centimeters of length. Now, the other thing you have to make sure is that there's exactly a 90-degree angle between here and here. We can't eyeball it. You have to measure it. So grab your protractor. You can turn it whichever way you like, but you want to make sure that there is a 90-degree angle between the vertical arrow and the horizontal one. They should be perfectly perpendicular. Okay. 90-degree angle in there. Okay. That gets you through step A1. Now let's look at A2, which asks you to draw in the displacement. So when you draw in the displacement, it's that green vector right here. So you're just connecting these 2 points together with your ruler. You should have had an arrowhead that's pointing here, and you should have labeled that D with the arrow over the top, just like we did in our practice questions. Now, part B asked for the magnitude of this. The intent, because you drew it, was for you to measure it and use the scale. Okay, we're not supposed to use Pythagorean theorem. So when I do this and I measure it, I'm getting 7.2 centimeters. So 7.2 centimeters in this scale would be 360 meters. You're given about 15 meters of leeway on that answer, which means that we will accept answers between, I have the range written somewhere else. We're going to allow answers between 346 and 376 meters. This was the range that the New York State Regents exam gave that year, because this was a question on a Regents exam. And then in part C, they want the angle in degrees between the north and the displacement. This is different than what we were doing in class. In class, we always measured from the positive x, which is the east. Here they want it from the north. which means I want this opening right here, that opening right there. So when I do that with my protractor, to measure that opening, we put our origin at the origin on the picture and we line up the vertical with 0. Line up the vertical with 0. And then we measure from here to here, and you can see I'm getting 56 degrees when I do that. You're given 2 degrees of leeway on that angle. Okay. Any questions on this or any of the other problems that were assigned before we take a quiz? How'd you do on the drawing one? Decent? Okay. All right. No questions on any of the multiple choice? Feel good about them? Okay. Then what I'd like you to do is keep your packet open to page 9. You've got a lot of blank space on that page. You can use that as scrap paper for today's quiz. And our quiz, again, is in a Google form. So you'll need your Chromebook now to take your quiz. You can have all the stuff that's up on the chalkboard there to help you with your quiz in the Google form, okay? Good luck. All right. I think everybody's done. Yes. Okay. You are going to need your Chromebook for this next part of things. Lab 4. So if you could please open up to Lab 4, which we were working on last week. We're going to finish it and get it turned in. If you're paying attention, following along with me, you should get 10 out of 10 on this lab because we're going to answer all the questions together. So I want you to help answer them. I'll just type them on the screen. You can type them down yourself. Doesn't mean I don't want you checked in to what we're doing. Make sure you're staying checked in as we work on this. I'm doing it kind of selfishly right now. It just makes it a lot easier for me to grade. And grading labs is probably the least favorite thing I do in my job. I don't like to grade labs. I like to do labs. I hate to grade them. But anyway, if you remember this lab with those little buggies out in the hallway, what we did last week was we first created our position time data table where your group had to get those Post-its down in the hallway pretty quick, right? And measure out those positions. Maybe next year, instead of every 2 seconds, I'll have you do it like every 3 seconds. That might be a little bit easier. But anyway, there they are. We then created our position time graph, which you should have. It should look like this on the experiment tab. And then we had time. Had enough time. We were able to write the equations for all 6 cars. And I think we even went over them, right? We're good. So that tab is completely filled out. Let's go to the analysis tab then. This is where we're going to pick up. And we're going to answer the questions on this tab together, referring to the graphs that we just made. So the first 5 questions just want us to look at the graphs for car 1 and car 2. So if we look at the graph here on the experiment window, for car 1 and car 2, car 1, the legend says that's the bright blue dots here. And here is car 2. And that first question asks us if these data points are creating a fairly straight line. What do you think? Are those data points creating fairly straight lines? Yeah. Okay. So let's answer that question. Yes, the data points are creating straight lines. Okay, now question 2. This one I'm going to have to help you with a little bit. Question 2 is asking us about what physical quantity is represented by the slope of a line on a position time graph. So let's look at these graphs for a minute. Car 1 is the bright blue, car 2 is the red. There is the slope of car 1, which we said in our equation was positive 14.6 centimeters per second. And here is car 2, which we said was positive 42 centimeters per second. Obviously, they have different slopes. Notice that car 2 has a larger slope, and that graph is steeper. If the groups that had car 1 and car 2, raise your hand, please, if you had car 1 or car 2. Okay. We started them both down this end of the hallway, right? And then they went this way, but something was different about how they were moving this way. Do you remember what was different about them as they were coming down the hallway? Those 2 groups might remember because they were side by side. You recall how the other buggy moved in comparison? Yeah. Do you remember which one was faster? Yeah, the second one. Now take a look at that graph for car 2. Something about car 2 is larger on that graph. What is it? The slope. It's steeper, right? So that slope has something to do with how fast it's going. Now in physics, the slope on these graphs gives us something called a velocity. What a velocity is, and this is going to get formalized in our notes in just a few minutes, velocity refers to the speed, meaning how fast you're going. But you remember we put positive and negative signs on the slopes? The positive sign was telling us it was going that way, a direction. So a velocity not only tells you how fast you're going, it tells you in what direction you're moving. So the positive sign was telling us it was going that way. And if we think about, if we were let's say this was a glass wall instead, and we could see the hallway, and we're looking that way. This way is which way? To the right. And if it was going that way, it would have been left. Okay, so those two cars were both traveling to the right, which is indicated by the positive nature of their slopes. But because 2 is steeper than 1, it's going faster. Both going to the right, but 2 is going faster. So number 2, we can answer now. The physical quantity that's represented by the slope is the velocity. So the velocity, meaning the speed and the direction of motion, is represented by the slope. So the slope is the velocity, or the velocity is the slope. And what is velocity? It's your speed and direction of motion. All right, so let's look at number 3. Question 3 says, how do the slopes for those two graphs compare? And what does that mean? Now, anytime we use the word compare in a question, it's implicit that you should be telling me something about them that's the same and something that's different. So let's look at those two slopes. Car 1, car 2. Want to tell me either one? Something the same or something different about them? Anson? So what does that mean? Yep. And in what direction in this case? To the right. So they're both positive slopes, which indicates they're both moving to the right. Okay, now we need the different part. What is different about them? Yeah, it's got a larger slope, which indicates the line is steeper, which indicates what? It's faster than the other car. Very good. Okay, let's answer both parts of that for this question. So both of the slopes are positive, indicating they are both moving to the right, but car number 2's slope is larger, which means car number 2 is moving faster. Does that make sense, everybody? So the number itself is your speed. The sign is which way it's headed. So are these velocities for both cars constant or not? And how would we know? So if I look back at the graphs, remember, how would I determine if the velocity is constant? The velocity is the what? The slope. So if the velocity is constant, the slope should be constant. So the line, let's look at car 1. Is the slope of the line from 0 to 4 the same as the slope of the line from 4 to 8? Is it the same from 8 to 12? Is the slope, the steepness, the same? It's just as steep all the way through. How about the red one? From 0 to 4, 4 to 8, 8 to 12, just the line. Are the slopes the same throughout? Yeah. You're not changing the steepness, the pitch of the line. It's the same throughout, which means the slope is constant. So are the velocities constant? Yeah, they have to be because they are the same things. Okay, so the velocities are constant because, I spell because right, because the graphs are lines and lines have a constant slope. The slope of a line doesn't change as you go along the line. So the next question, 5, asks how we would recognize a position time graph for an object that's traveling at a constant velocity. What would we be looking for? when I look at these graphs, how can I tell that these two are traveling at a constant velocity? What's the shape of those graphs? All lines are straight. Diagonal lines. They're both diagonal lines. So objects that move with a constant velocity appear as diagonal lines on a position versus time graph. So if we see a diagonal line on a position time graph, that's going to indicate that we have a constant slope and therefore a constant velocity. Okay? Okay, questions 6 and 7 and 8 are referring to car 3 and car 4. So let's go back to those graphs and let's see. Car 3 is the one in yellow. Car 4 is the one in green. You see them? 3 and 4. All right, let's look at the first question. What do you notice about the shape of those graphs? Is the shape similar to the graph for car 1 and car 2, or is it different? So what would you say the shape of the graph for 3 and 4 is? What's the shape? Name it. Diagonal lines. What did we say the shape was for 1 and 2? Is it the same or different? It's the same. Okay. So the graphs for car number 3 and car number 4 are also diagonal lines. What now? It says explain. What that means, what does that mean? What does that mean since the graphs are diagonal lines? What does that mean about car 3 and car 4? Look back at question number 5. Since these are also diagonal lines, what does that mean? Really? That's right. That's what that means. So these cars are also moving with a constant velocity. Okay, so now let's look at the slopes for 3 and 4. I want you to compare the slopes for car 3 and 4 to car 1 and 2. So here's car 3, there's car 3's slope, there's car 4's slope. What do you notice that's different about them? 3 and 4 have what type of slope? Negative. So what does that mean? Yeah, it means that these cars were going left, whereas car 1 and 2 were going to the right because they have positive slopes. Very good. Okay, so the slopes for car number 3 and car number 4 are negative. This means they were moving to the left. Car number 1 and car number 2 had positive slopes, which means they were moving to the right. Now let's look at the last question here. Is the velocity of car 3 constant or not? And what about the velocity of car 4? And how do you know? Is car 3's velocity constant? That's the one in yellow. Yes, right, Liam. How do you know? All lines are straight. It's a, what type of line is it? Diagonal line. What about 4? Is that traveling with a constant velocity? Yes, because it's a diagonal line. There you go. So the velocities are constant because their graphs are diagonal lines. Now, when you finish typing that, make sure you hit enter and move out of the cell. You should see that your response has been saved. If you stay in the cell and don't hit enter and you go somewhere else, when you go back, it's going to be blank, which has happened to a couple of you on previous labs. You've submitted things with a blank, and that's because you didn't hit enter or move out of the cell. Google Sheets does not save your work until you move out of it. All right? That's just the way it works. It's not like a Google Doc where anything you type gets saved. All right, can we go to the conclusions? The conclusions is sentence completions, filling in the blanks. These are the patterns that we should now recognize looking at these graphs. So if you have a linear position versus time graph that tells you the object is moving with a, what did we just say? If we have a line, the object is moving with a, look back, diagonal lines. What does that mean? Constant velocity. There you go. They're moving with a constant. And it is in red and italics. I would like it to be that way so I can clearly see your answer. All right. It's like calling attention. Here's my answer, Ms. Famoso. Easy for me to grade. Number 2, what does the slope of a linear position time graph tell you? The slope gives you the what for the object? The velocity. That tells you the velocity of the object. And what is a velocity? It's the speed and direction of motion. All right, we didn't talk about this, the y-intercept. So if I look at a position time graph, let me go back to that for a minute. Here are my y-intercepts. Those are the y-intercepts right here. What are those y-intercepts telling us about each car? They're what? Their starting position. We actually call that the initial position, the position at time 0. So it's telling us the initial position or the starting point of the object. Where was the object located at time 0? That gives you your y-intercept, your initial position. So based upon what we just learned, the faster the object is moving, the what for the object's position time graph? The faster you're going, the what for the graph? The steeper, right? The steeper the object's position time graph will be. So the slower the object is moving, the blank the object's position time graph will be. Shallower, right? Shallower is opposite of steeper. If you have an object traveling to the right, it has what type of slope on the position time graph? I'm hearing conflicting answers. You want to duke it out? Positive, yeah. It's a positive slope. And if you're traveling left, you're going to have a negative slope. Again, make sure you hit enter, move out of the cell. So move around. It should stay there. Your answers should all be there. Check that for the analysis as well. Everything is filled in. There are no blanks, right? Nothing is blank. Check on the experiment tab as well. Nothing here is blank. If anything is blank that's shaded in yellow, that's losing points on the lab. That's what I'm grading. Any questions on this lab? All right, then please turn it in Google Classroom. Turn it in, please. And then you can put your Chromebook away. Okay. And what we're going to do now is we'll need our notebook and our reference table and something to write with, please. And what we're going to do now is start section B of Unit 2, which is about these position time graphs that we've just created, and what does it all mean? All right. So Unit 2B is all about position versus time graphs. Okay, let's do a little review. When we talk about position, remember we're talking about where an object is located. And in this unit, we're going to say on the x-axis. Where is it located on the x-axis? We eventually might go to where is it located on the y-axis, or where is it located on the xy coordinate system. We did a couple of those, if you remember, initially. But right now, we're just going to deal with the x-axis. So let's please draw an x-axis. This is our positive x direction. And I'd like you to label some points here. These are all going to be in meters, okay? So 0, plus 1, plus 2, plus 3, plus 4, negative 1, negative 2, negative 3, negative 4. Which means that if I had an object located right there, I would say that the position is positive 3 meters. Another way to say that, we would say we were 3 meters to the right of the origin. Okay, let's take a break. And when you come back, we'll work on more notes on this. All right, so let's continue. We just talked about this object here. That's position would be positive 3 meters, which means 3 meters to the right of the origin. Now, since we're dealing with just the x-axis, I could use the symbol X to represent that position. It's the X coordinate. Now, in terms of trying to create a position time graph from this information, what I want you to do is kind of envision taking this and rotate it by 90 degrees, which means that that x-axis now becomes the y-axis of a graph, which we're going to label position in meters. Here's the horizontal axis, which will represent the time in seconds. So the title of this graph would be position versus time. This is our origin. And then what I would do is I would label these positions here. If I take this and I flip it 90 degrees, it means that I'd have positive 1 here, positive 2 there, positive 3, positive 4, negative 1, negative 2, negative 3, negative 4, and so on. And these would be the times at which we were located at various positions on the x-axis. So if I wanted to graphically represent this position, let's say that's where I was when I started timing the motion. I would be putting this point right there on my y-axis. Okay, because that's my starting position. My y-intercept is the starting position, initial position, we call that. Does that make sense? So instead of being to the right, when we graph it, it ends up going on the y-axis, even though it's x right and left motion. All right, let's name these variables. Since position is on the y-axis, that is our dependent variable. Since time is on the x-axis, that is our independent variable. So far, so good? Okay. Then let's talk about some things that we can determine from this graph once I have multiple points on there. And I want to reintroduce the term velocity. What is velocity? Right? Because we just talked about that in the lab a minute ago. So the first thing I would say to define this, we would be talking about how fast an object is moving. And when we talk about how fast something is moving, we're talking about its speed. When we say how fast, we're talking about an object's speed, but it also includes something else. So it talks about how fast and, yes, the direction of motion. Or the direction the object is moving in. Since it has a numerical value and a direction, we call this a vector measurement. Remember that term, vector? Ring a bell? If it's a vector measurement, it's going to have two things. It's going to have a magnitude, which we said is synonymous with a size or an amount. In this case, that's referring to the speed of the object, how fast it's going. But it's also going to have a direction on the measurement, which indicates the direction of motion. Which way are you moving? Now, the symbol that we're going to use to abbreviate velocity, instead of always writing it out as a word, we're going to use V with an arrow over it. I think the V makes sense, right? V, velocity. But we put the arrow over the top to remind us that it is a vector. The units that we measure velocity in the metric system are meters per second, which we can abbreviate as M over S. All right. Since we've talked about speed, we should probably define that. So what is speed? When we talk about speed, we're just talking about how fast an object is moving. How fast are you moving? Since we are not talking about any kind of direction with this measurement, do you remember what we would call it? What type of measurement we would classify it as? Not a vector, but a scalar. That's right. This is a scalar measurement, which means there's only a magnitude. Only an amount or a size. There's no direction on it. Like velocity, the symbol that we're going to use to represent speed is a lowercase v. We just don't put the arrow over the top of it. So by using the same letter, it means that they are related to each other. They're related. But this is the scalar because there's no arrow. That is the vector because it has the arrow. Make sense? Okay. The units that we're going to measure this in, metric system, are meters per second, which again is abbreviated M over S. Now, in the United States, remember, we are more familiar with using English customary units, not the metric system. So we don't use meters per second on our speed limit signs. We use miles per hour. That's a speed. It's a length measurement over a time measurement. That is a speed. All right, let's play a little game here. I'm going to give you 4 measurements, and I want you to classify them for me. What are these measurements of? Can you tell me what each of these is a measurement of? Can you tell me what any of them is a measurement of? You identify them. What are they measurements of? Any of them. Anybody think they know any of them? Any of the 4? Liam?
4 is direction.
No. That's a distance. There you go. Letter D for distance. What are the other 3? Maureen? Yep, number 1 is a velocity. It's in meters per second, and it has the direction. So that's velocity. Aiden? Right, that is a speed. Units are meters per second, no direction on that, so that's just a speed, V. What is number 3, Liam? That's a displacement. It's got a length in meters, but it also has a direction with it, so it's a displacement. Very good. So that we're kind of bringing together what we were quizzed on today with the new stuff today. We have to be able to look at those and identify them. All right, can we go on? Can I go to another page? I now want to talk about how you get velocities from a position time graph. Now remember, since we are working with positions on the x-axis, I could just say this was a graph of X versus T. Okay, how are we going to get a velocity from one of these position time graphs? Do you remember from the lab what we said we do? What gives us the velocity when I'm looking at a position time graph? The slope. It's the slope. The slope is our velocity, which again means it's going to tell you how fast you're moving, your speed, and it's also going to indicate to you which direction you're moving in. What direction are you headed? All right, so let's do some patterns. Do you remember from the lab, if you had a positive slope, what does that mean? Yep, that means you're moving to the right. If you have a negative slope, what's that going to mean? Carolyn? That's right. All right, this one we didn't talk about, but let's see if you can figure it out. What if you had a 0 value for the slope? That's not positive or negative. What does that mean? Right, so what does that mean about the object? That means you're not moving, right? That would mean you're not moving at all. If you had a large slope value, meaning the graph is very steep, what would that mean? You see a steep line on your graph. What's that going to mean? Jacoby? Yep, that means you're moving fast. Versus if you have a small slope, that's going to look like a shallow line. Felucci, what's that going to mean? That's right. That's going to indicate that you're moving slowly. And one final thing we discussed was the meaning of the y-intercept. What's the y-intercept going to tell you? Your initial position. That's right. Which, again, we kind of said that's the same as your starting point. Where are you located at time 0? Okay. What I'm going to do now is I'm going to create a sketch of 5 position time graphs. And I want us to try to describe the motion that each of these graphs is trying to communicate to us. Okay. So here's what we're going to do. Let's make a graph, sketch it. We don't need graph paper. We're just making a quick sketch. This is going to be the position in meters. This is going to be the time in seconds. So our title would be position versus time, or X versus T. All right, I got to move this down here a little bit. Sorry. All right, so let's see. I'm going to label each of these lines. Line 1. Line 2. Line 3. Line 4. And line 5. I got to zoom out, I think. There we go. Can you see all 5 of those? Okay, let's start with line number 1. Anybody tell me what object 1, the graph for object 1, is telling you, Liam? Yep, this object is not moving. It is a horizontal line. A horizontal line has a 0 value for the slope. It is not moving. Has no speed. Okay, let's look at object 2. First of all, can you tell me which way it's headed? It's headed to the right. How do you know that? Positive slope. The line is going up, so that means it's headed to the right on your number line. Is this line steep or shallow? So what does that mean? Okay, so the way we would describe the motion of object 2 is it's moving to the right with a slow, constant velocity. I know that the velocity is constant because I have a line. If I don't have a line, then the velocity isn't constant, but that's not this unit. Everything we see right now is going to be a line. Okay. Let's talk about graph 3. Could you write a description of graph 3 in comparison to number 2? Can you do that for me? I would agree with that. This one is also moving to the right. With a fast, constant velocity. All right, let's now look at 4. Anyone want to try to write a statement about number 4? Try to use like parallel structure to what we did in 2 and 3. Caroline? I would agree with that because of these 2, 4 is shallower than 5. So this one is moving to the left. With a slow, constant velocity. Tom, you want to try number 5? Yes, that is correct. Very good. It's going to the left because it has a negative slope. And it's going fast because the graph is steep. So those would be descriptions of the motion of each of them. All right, I've got another question for you. What can you tell me about the initial positions for objects 1, 2, and 3? Yep. So this tells me that all 3 start at the same point. All 3 of those were located at the same point when we started timing motion. All right, here's my next question. Which of these objects started furthest to the left? Which one started furthest to the left? Morgan? Yeah, 5, because it has the most negative. 0 is the most negative of all of those. So this one, I don't want to label it there. Put it here. Starts furthest to the left. And in fact, if I were to take that position axis and rotate it 90 degrees like this, I think you can now see it. You see how that is the furthest left of all the points there? We have a point here, a point here, and a point here. These are all starting at the same point on that horizontal x-axis. That is the furthest left of the 3. Does that make sense? You just rotate it around. You've got paper. You can easily do that to help you understand it. All right. Of the 5, which one is the fastest of the 5 graphs? And how do you know? Brayden? It's the steepest out of all of them. Yeah, 3 is the fastest to the right. 5 is the fastest to the left, but 5 is even going faster than 3 because it's an even steeper line. It doesn't matter if it's up or down. It's just the pitch. How close to the vertical is it? So 5 is the fastest of all because it is the steepest one on our sketches. Okay, I've got one more thing to do with you and we're done. Okay, can I flip the page? So what does the slope of a position versus time graph equal? Velocity. And remember that velocity refers to the speed and the direction. All right, let's review. How do you find slope?
Pick 2 points and subtract the second one from the first one.
Okay, so can you tell me what equation I should be writing to find slope?
Slope equals y2 minus y1 over x2 minus x.
Good. Now let's say this is my graph of my position in meters versus my time in seconds. Let's say I've got a line on this graph, okay? Diagonal line like that. This is my starting time. I'm going to call that TI. And this time here would be the final time where I stop timing the motion. This value here would be my initial position, XI. I think you've seen these symbols before, XI. Initial position, the y-intercept. And this coordinate here, which is the y-coordinate for that point, would be my XF, my final position. Which means that if I were to change out the letters here, slope is velocity. Do you remember what symbol we use for velocity? I'll help you out. It starts with a V. What else is there? The arrow over the top. All right, so we have V with the arrow. I'm changing slope to V with the arrow. The second y coordinate, this is 0.1, that's 0.2. The second y coordinate is what we call our final position. The first y coordinate is what we're calling the initial position. The second x coordinate is our final time. The initial x coordinate is what we call our initial time. Oh, hold on a minute. Anybody remember what a difference between the final and initial positions is called? You might want to look back in your notes. What do we call XF minus XI? That is called the displacement, which is D with the arrow. And this is what we call the time or the time period. So we just developed a physics equation from a graph, which I'll show you in just a minute on our reference table. So one last thing to talk about is that when we have constant or uniform motion, on a position versus time graph, you're always going to get a line. It's always a line, but there are two kinds of lines you could see. You could have a horizontal line, or you could have a diagonal line. If you have a horizontal line, what does the slope equal? 0, which means that you are not moving, because that implies the velocity is 0 meters per second. A 0 meter per second velocity means you are not moving. If you have a diagonal line, that means your slope does not equal 0. So your velocity is not 0. This means, therefore, that you are moving with a constant velocity, meaning your speed is constant and you aren't changing direction of motion. You are not changing in what direction you're headed. You are always headed to the right, or you are always headed to the left. That's it. Okay. That's it for the notes. I'd like you to look at your reference table for a minute. Can we please turn to page 6? We have some things to check off today. Okay, let's start in the right-hand column. So today, well, we used the letter D for displacements or distances. We have 2 additional ones we're going to check off today in the right-hand column. We're going to check off the letter V. Do you see it here? V. Velocities, or it could mean speed. Velocity is the vector, so that's the one I'm going to put the arrow over. Both of these are measured in what units in the metric system? Meter per second. So let's add that. So when we see something in meters per second, if it has a direction, it's the velocity. If it doesn't, it's the speed. The other variable I just introduced to you is the variable t. The amount of time over which we're making measurements, we call that a time interval. This is going to be measured in seconds. And if you note, the equation we just developed right here looks a lot like an equation we see on the reference table right here. Please check this one off. This is the first equation we're going to be working with starting on Wednesday. That we can get the velocity if we take our displacement and divide by time, or we can get our speed if we take the distance and divide by time. Depends on if we have vectors or scalars in there, what we're getting. Okay, but we'll learn more about that on Wednesday's class. The video I've got ready to push it out will talk all about that equation. All right, any questions for me right now? All right, let's see how we're doing. What time is it? I got 10 minutes. Here's what I want to do. I know we've done a lot today, but I want to try to push ahead so that way I can give you tomorrow's class at the end, time to work on the homework. Because there's no written homework tonight. It's just studying. I don't want to give you 10 minutes to study right now. Instead, I'd rather use that time to push ahead so that way tomorrow you have time at the end of class to work on the written assignment. How's that sound? Okay. So could you please pull out your packet for Unit 2 and turn to page 10. Has this worksheet. We'll just get started. We're not going to finish it. This is really tomorrow's lesson was those 2 pages, but since we're there, let's do it. All right, so this worksheet asks us to consider the position versus time graph below for 2 cyclists, cyclist A and cyclist B. There's cyclist A, there's cyclist B. Let's see if we can answer these questions based on this position time graph. Remember, position is the variable X, time is the variable T on the grid. So, part A, are these cyclists starting at the same point? Can you tell me? Look at that graph. Are they starting at the same point? No, that's right. So the answer to this is no. How do you know they're not starting at the same point? What is it? That's right. They have different y-intercepts. So which cyclist starts ahead? Which one? Yes, how do you know? Yeah, it has the most positive y-intercept. So cyclist B starts ahead of cyclist A because it has a more positive y-intercept. Okay, letter B. At 7 seconds, who's ahead? So here's 5 seconds. 7 would be over here. Who's ahead now? So if I said this is 7 right about here. Who's ahead now? Liam? How do you know? Because it has a more positive y coordinate. Yep. So cyclist A is now ahead of cyclist B. The y coordinate for A is greater or more positive. Which cyclist is traveling faster at 3 seconds? 3 seconds would be like right about here. Who's going faster here? A or B? I heard somebody say it. Or they think their answer. Who's going faster? Okay, can't be both. When I say how fast, that's referring to the speed. Speed is in the slope. Which one is steeper at 3 seconds? A. So that has a greater velocity and therefore a greater speed. It's going faster. So A is moving faster at 3 seconds. The slope is greater, or another way to say that is the line is steeper. It's steeper. Are their velocities equal at any time? Velocity is the what on this graph? The slope. Are the slopes, the steepness the same any point on these graphs? No. And how do we know? They are always different slopes. Or they never have the same steepness. So can you tell me, therefore, A and B intersect at 5 seconds, right? What is that point of intersection telling you? Anson? That's right. They are at the same position. That is where cyclist A catches up to B. And then eventually passes them at that point. Good? All right, tomorrow we will do page 11. And that's all I got for you for tomorrow is page 11. So we're doing really good. You're going to have a lot of time tomorrow to work on the assignment. Get this back here. So tonight, please, please, please study the notes that we did today. We did a lot, but it's helpful if you study a little bit so that way tomorrow we're not starting over. Okay, I really don't want to have to repeat what I taught you tomorrow or what I taught you today. I don't want to repeat it again tomorrow. So please